Look at our world from space. At night, it glitters with a light that mimics the stars. A vast, interconnected web of crystalline structures we call cities. We see them as our legacy, our defiance of nature's chaos. Towers of glass and steel that tear holes in the clouds, rivers of concrete and asphalt that stretch from one horizon to the next. We have carved our civilization into the very skin of the planet, crafting monuments of such scale they seem destined to outlast us by millennia. They are our fortresses of permanence, our shout against the entropy of the universe. But this is a grand illusion, a story we tell ourselves, because in the eyes of biology, our immortal cities are not fortresses. They are not monuments. They are the single largest, most concentrated, and most unnaturally rich deposit of food in the history of the planet. Every material we have forged is living on borrowed time. Every steel beam is just refined iron or a substance so unstable in the presence of oxygen that it desperately wants to revert to its natural state. Rust. Every pane of glass is just sand, momentarily frozen in a state of transparent limbo before the slow, grinding process of weathering turns it back to dust. And concrete, the very bedrock of our civilization, it's nothing more than artificial rock, but a flawed and porous imitation. It is riddled with microscopic capillaries, invisible highways that eagerly wick water deep into its core. We see these materials as eternal, but they are merely molecules in a state of high-energy tension, waiting for a nudge to collapse back into chemical equilibrium. We didn't invent new elements, we just rearranged them. And anything that can be arranged can be rearranged. The most tempting targets, however, aren't even the minerals. They are the polymers, the plastics, the rubbers, the vinyls, the endless chains of hydrocarbons we have wrapped around our world. Look at an asphalt road. We see a durable surface. But what is it chemically? It is bitumen, a thick sludge of long-chain hydrocarbons left over from refining oil. It is, for all intents and purposes, the compressed and distilled essence of ancient sunlight, the fossilized remains of trillions of prehistoric organisms. We have taken the most energy-dense substance life has ever created and paved our world with it. We have built a global buffet of pure carbon energy. This isn't a metaphor. It is a chemical fact. We have inadvertently created the most accessible and widespread food source this planet has ever seen, and for a century, nothing has had the key to unlock it. But evolution has solved this exact problem before. For 60 million years during a period known as the Carboniferous, the planet was covered in vast swampy forests. Trees grew to enormous heights, died, and fell over. But they did not rot. They simply piled up, layer upon layer, because a crucial piece of biological machinery was missing. Nothing on Earth could effectively digest lignin, the incredibly tough and complex polymer that gives wood its strength. The evolution of this natural plastic had outpaced the evolution of decomposers. The result? The dead forests were buried, compressed, and cooked into the colossal coal seams we burn for energy today. They became a geological layer, not a biological one. Then, everything changed. A new kingdom of life, the fungi, finally cracked the code. They evolved the specific enzymes, the precise molecular scissors needed to snip apart the lignin polymer. And with that, the age of coal formation slammed shut. Life had caught up. It had found the key. It always does. That exact same story is beginning again, but on our timescale, not a geological one. The warning shot was fired in a plastic recycling plant in Japan. There, scientists discovered a humble bacterium, Ideonella sicyensis, doing the impossible. It wasn't just surviving in a plastic-rich environment. It was dining there, and it wasn't a crude, brute force attack. This bacterium had evolved a sophisticated two-step chemical weapon. It secretes an enzyme called PEtase, which latches onto the surface of a PET plastic bottle and breaks the impossibly long polymer chains into smaller, manageable molecules. But it doesn't stop there. It then uses a second enzyme, MHEtase, to slice those smaller molecules into their most basic edible building blocks. It's a precision chemical disassembly line that turns our most common plastic into simple sugars. And the most terrifying part? Genetic analysis suggests this entire complex system evolved in just a few decades. It is evolution running at blinding speed. While this new war is being waged against our polymers, an ancient, silent war against our stone and metal rages on. The world is teeming with microorganisms known as lithoautotrophs, literally, rock eaters. These are the true masters of inorganic chemistry. They don't need sunlight or organic matter. They breathe minerals. Bacteria like thiobacillus thrive on sulfur and iron compounds, and their metabolic waste product is one of the most corrosive substances known: sulfuric acid. When these microbes colonize the surface of concrete, they are not just living there. They are actively dissolving it, leaching the calcium from the cement and turning our artificial rock into a soft, crumbling paste. They do the same to metal, accelerating corrosion at rates that defy our engineering models. We see a rust stain on a bridge girder as a simple chemical reaction with the air. In reality, it is often the footprint of a thriving microbial colony that is actively feasting on the iron. So what does this mean? It means our cities are not the sterile, lifeless landscapes we imagine them to be. They are a biome, a novel, man-made ecosystem that we have seeded with life from every corner of the globe for over a century. Every shipment of fruit, every gust of wind from a distant forest, our own bodies. We have been the vectors, inadvertently populating our concrete jungles with a diverse library of microbial toolkits. We have laid out a global banquet of never-before-seen materials, and then we have scattered the genetic blueprints for how to consume them right on top. We created the challenge, and we also provided all the necessary parts for the solution. The stage is set for an evolutionary masterstroke. The only thing separating our world from this biological meltdown is specialization. The plastic eaters can't yet dissolve concrete. The rock eaters can't yet digest asphalt. They are individual specialists working in isolation. But in the microbial world, secrets are never kept for long. Through a process called horizontal gene transfer, bacteria and fungi are constantly swapping DNA. The gene for the P-tase enzyme from Ideonella sicyensis can be copied and transferred into a lithoautotroph that already knows how to produce acid. The result would be a single organism that can eat both plastic and concrete. A microbe that sees our entire urban environment, from the PVC pipes in the ground to the steel beams in the sky, as a single continuous meal. This isn't a question of if. It is a question of when. Evolution is the greatest problem solver in the universe, and we have just presented it with the ultimate puzzle. How do you dismantle a world? The clock is ticking, and the answer is being assembled, right now in the dirt and dust at our feet. Imagine a place where the rules of nature are broken and rewritten every single day. A place with more chemical diversity and violent pressure than a deep-sea hydrothermal vent or the caldera of a volcano. This isn't some distant, alien world. This is our landfill. We see it as a graveyard, a final, forgotten resting place for the things we discard. But for microbial life, a landfill is a supernova of chemical chaos. It is an evolutionary accelerator, a biological gladiator pit running at 1,000 times the normal speed, and it is the perfect cradle for creating a monster. The process begins with a great dying. When a wave of industrial solvents or a mountain of shredded plastic buries a section of the landfill, 99.99% of the microbial life in the soil is annihilated instantly. But some survive. These are the extremophiles, the ultimate survivors of the microbial world. They are organisms that, through eons of evolution, have learned to thrive in conditions that would sterilize a hospital, boiling hot springs, deep-sea trenches, even the cooling pipes of nuclear reactors. In the landfill, these specialists in survival find themselves in a new kind of hell, and they are the only ones left standing. This intense, brutal filter of selective pressure is the first step. It clears the board of all the normal players, leaving only the toughest, most resilient freaks of nature. For these survivors, the toxic wasteland is also a land of unimaginable opportunity. This chemical soup is a buffet of high-energy molecules. The long, ordered chains of carbon in a polyethylene bag, the complex rings in a styrofoam cup, the phthalates in a vinyl sheet, these are incredibly energy-rich structures. They are locked safes, and most organisms don't have the combination. But for the extremophile that randomly mutates the right enzyme, or already possesses a tool for a similar-looking natural molecule, it has just hit the evolutionary jackpot. it gains access to an all-you-can-eat feast that no one else can touch, allowing it to multiply at an explosive rate. Into this chaotic arena steps the perfect candidate for a future predator: a fungus. Its ancestors are the humble molds, organisms we find on decaying logs or old bread. Fungi have three key advantages that make them uniquely suited for this role. First, they are masters of external digestion. They don't ingest their food. They secrete a powerful cocktail of enzymes onto it, breaking it down externally and then simply absorbing the nutrients. Second, their bodies, the vast, hidden networks of threads called mycelium, are built for exploration and invasion, capable of patiently probing and penetrating the toughest of surfaces. And third, their cell walls aren't made of soft cellulose like plants, but of chitin, the same tough, resilient material that makes up the exoskeletons of insects. They are, in essence, natural-born armored decomposers. But evolution here isn't just a slow, plodding march of random mutation. The microbial world has a superpower, a biological internet for swapping tricks and weapons. It's called horizontal gene transfer. It happens in several ways. Sometimes bacteria package useful genes, like the one for a plastic-digesting enzyme, into small circular pieces of DNA called plasmids. These plasmids function like genetic trading cards, passed from one microbe to another, even across different species. Other times, viruses that infect bacteria, known as bacteriophages, accidentally snip out a piece of their host's DNA and carry it with them, injecting it into the next victim. This isn't inheritance, it's theft. And in the dense, competitive soup of the landfill, it's happening billions of times a second. A fungus can acquire a gene for digesting PVC from a bacterium, a gene for neutralizing mercury from an archaean, and a gene for resisting acid from another fungus. This is how our predator Petromyces vastator is assembled. It is not one species evolving in isolation. It is a living mosaic, a Frankenstein's monster of evolution built from the best stolen parts. It combines its own innate fungal toughness and invasive power with a crowdsourced library of chemical weapons. It learns the trick for breaking down polyurethane from one neighbor and the secret to metabolizing nylon from another. Evolution, acting as a blind tinkerer, is taking the most effective genes from hundreds of different specialists and stitching them together into one unstoppable generalist. This organism is no longer just a fungus. It's a walking database of decomposition, with the genetic keys to unlock almost any synthetic compound we've ever created. The Petromyces that finally outcompetes all its rivals is a different kind of life form. Its hyphae, the tiny threads of its body, are reinforced, capable of surviving solvents that would dissolve other molds. Its spores are encased in a resilient, polymer-like shell that allows them to lie dormant for years, waiting for the right conditions, immune to radiation and chemical attack. And its enzymatic output is a thing of biochemical horror. It doesn't just produce one or two types of enzymes. It secretes a complex, adaptive cocktail that can snap the carbon-carbon bonds of our most durable plastics, chelate heavy metals, and begin the process of breaking down hydrocarbons. It has been forged in the ultimate fire, tested against every poison we could throw at it, and has emerged with the tools to dismantle our world. It has learned the language of our chemistry. It sees our civilization not as a collection of inedible objects, but as a sprawling, interconnected network of nutrients. The city is no longer an obstacle. The city is the ultimate substrate, the final log to be decomposed. For millions of years, fungi have been the great recyclers of the natural world. Now, evolution has handed them a new, unprecedented task: to recycle an entire geological epoch. The Anthropocene. The fungus has been born, it has been trained, and it has been armed in its cradle of waste. But it has eaten everything in its toxic nursery. Now it is hungry, and it is ready to leave. The escape is not a dramatic event. There is no monster clawing its way out of the trash. There is only the wind, and a process as old as life itself. On a dry, blustery day, the mature fungal colonies in the landfill release their progeny. A single fruiting body, a structure no bigger than a dinner plate, can release over 1 billion spores in a single hour. They are not merely dust. They are microscopic spacecraft, each one a perfectly engineered vessel of genetic code, encased in a tough, resilient shell. They are so small and light that the slightest updraft can carry them miles into the atmosphere, where they join the invisible rivers of pollen, dust, and other microbes that constantly circumnavigate the globe. This aerial assault is just one of 3 invasion routes. The second is far more direct. Every garbage truck that leaves the landfill is a mechanical typhoid Mary. Its tires, with their deep treads caked in a sticky residue of dirt and grime, are perfect collectors for fungal spores. As the truck rumbles back into the city, it becomes a sower, pressing these microscopic seeds directly into the asphalt streets, junction by junction, block by block. The third route is subterranean. Rainwater percolating through the landfill becomes a toxic soup called leachate, which is now teeming with spores. This contaminated water enters the storm drain system, a labyrinthine network of pipes that acts as a ready-made circulatory system, delivering the infection directly into the city's dark, damp underbelly. Now imagine a single one of these spores, carried on the wind, as it ends its long journey. It lands on the sun-baked surface of a highway. For days, it lies dormant, a speck of dust waiting for a sign. Then the weather turns. A cool rain begins to fall, providing the first ingredient, moisture. As the water soaks into the porous asphalt, it awakens another signal. The spore detects the faint chemical signature of volatile organic compounds, or VOCs, slowly leaching from the bitumen. To the fungus, this scent is not a pollutant. It is the smell of food. It is the specific chemical trigger its ancestors evolved to recognize in the landfill, and the signal to awaken. The spore's tough outer shell cracks, and a single questing thread, a hypha, emerges. This is the beachhead, the first bite into the body of civilization. Asphalt is the perfect gateway material. Unlike the hard, crystalline structure of rock, bitumen is an amorphous, disordered mess of long-chain hydrocarbon molecules. It's a tangled, sloppy structure that is far easier for the fungus's enzymes to attack and dismantle. The growing hyphae release their chemical cocktail, snipping the long polymers into shorter, digestible lengths. The fungus feeds. It grows. It branches out, creating a tiny, circular network just beneath the surface, a fungal colony no bigger than a coin. To the naked eye, it is utterly invisible, indistinguishable from a simple oil spot or a patch of discoloration. Soon, the invisible becomes visible but not understood. A pothole appears on a road with unnatural speed. Maintenance crews find a strange, web-like pattern of microfractures that defies conventional explanation. A section of pavement feels strangely soft and spongy under the summer sun. City engineers are baffled. They run tests, analyze core samples, and blame a bad batch of asphalt from the supplier or an unusually harsh freeze-thaw cycle during the winter. They are trained to look for chemical and mechanical failures, not biological ones. So they do the only thing they know how to do: they patch it. They lay down a fresh layer of hot asphalt over the affected area, unknowingly creating a perfect, dark, insulated, and moisture-trapped incubator for the thriving fungal colony underneath. Trapped beneath this new cap, the fungal colony grows, and it gets hungry. But it does not expand randomly. The mycelial network is a remarkably intelligent hunter. The growing tips of the hyphae are covered in chemoreceptors, allowing them to taste and smell their surroundings on a molecular level. This process is called chemotropism. The fungus can detect the faint chemical gradient of plasticizers like phthalates leaching from a PVC water main buried 6 feet under the road. It tastes its destination in the soil. The entire network then reorients its growth, abandoning less nutritious dirt and rock, and focusing its energy on sending dense exploratory filaments directly toward the richer food source. It is not wandering. It is navigating. When the mycelium reaches the pipe, it has found a superhighway. The PVC, softened with these edible plasticizers, is an ideal food source that fuels a population boom. The fungus envelopes the pipe, forming a thick, slimy biofilm. It doesn't just eat the pipe. It uses it. The long, smooth, protected structure is the perfect conduit for rapid expansion. The mycelial network races along the outside of the water main, spreading through the urban underworld at 100 times the speed it could move through soil. It travels from one street to the next, from one neighborhood to another, using our own infrastructure as its personal transit system. It encounters other lines, electrical conduits sheathed in polyethylene, fiber optic cables coated in vinyl, cast iron sewer mains sealed with rubber gaskets. Each one is a new flavor on the menu, and another road leading deeper into the heart of the city. This is how the silent invasion is won. Not with a frontal assault, but with stealth and infiltration. The fungus has successfully colonized the city's circulatory and nervous systems, the vast, unseen networks that give it life. And by following these subterranean pathways, it has found its ultimate prize, the foundations of the buildings themselves. The infection has breached the city's outer defenses, bypassed its skin, and is now poised to attack the bones. The enemy is no longer at the gates. It has been inside the walls for months, silently spreading, consolidating its power, and preparing for the next, far more devastating, phase of its attack. The true power of a fungus is not in its bite, but in its embrace. Having infiltrated the city's foundations through a web of pipes and conduits, Petromyces vastator now begins its most insidious work. It does not attack its food source like a predator, tearing it apart from the outside. It becomes one with it, infiltrating it, suffusing it, and dismantling it molecule by molecule from within. The invasion is no longer about spreading. It is about consumption. The city is still standing, looking as strong as ever, but it is now suffering from a silent, systemic, and incurable sickness. The assault begins on the concrete itself. To us, concrete is a rock. To the fungus, it's a porous cage holding its food. The real strength of concrete comes from a complex crystalline matrix of calcium silicate hydrate, a glue that binds the sand and gravel together. The fungal biofilm, now thriving in the damp, dark capillaries of the concrete, brings in a demolition crew, acid-producing bacteria. These acidophiles secrete a steady drip of organic acids, which perform a devastating chemical trick. Through acid-catalyzed hydrolysis, these secretions dissolve the calcium silicate hydrate, breaking the molecular glue and turning the hard, strong matrix into a soft, chalky, and structurally worthless powder. It is a form of chemical cancer, metastasizing through the bones of the city. The external symptoms of this cancer are subtle and always misinterpreted. A maintenance crew on a bridge notices an area of spalling, where the surface of a concrete pillar has flaked away, exposing the steel rebar underneath. They see it, log it, and blame the usual suspects. A bad pour, winter salt corrosion, or the relentless freeze-thaw cycle. They patch the surface with fresh concrete, a cosmetic fix that is utterly useless. They are treating a skin lesion, unaware that the patient's entire skeleton is being eaten away from the inside. The patch simply seals the infection in, creating an even more ideal, dark, and humid environment for it to thrive. While the acidophiles dissolve the cage, another team of specialists goes to work on the creature trapped within. The steel rebar. Deep inside the concrete, where oxygen is scarce, the biofilm creates the perfect environment for a different kind of microbe, sulfate-reducing bacteria, or SRBs. This is the science of microbially influenced corrosion, and it is far more aggressive than simple rust. The SRBs don't need oxygen to breathe. Instead, they metabolize sulfates present in the concrete and groundwater, and their waste product, their exhale, is hydrogen sulfide gas. This gas is fantastically corrosive to iron, initiating a chain reaction that pulls iron atoms directly out of the steel. This is not the slow, uniform peel of orange rust we are used to seeing. The corrosion caused by SRBs is a vicious, targeted attack. It creates deep, narrow pits that burrow into the rebar, hollowing it out from the inside like a termite eating wood. The steel's vital tensile strength, its ability to bend and flex under load, plummets. A 1-inch thick bar of steel can be compromised in a fraction of the time it would take for normal oxidation to have any meaningful effect. The city is developing a case of severe, galloping osteoporosis. Its mighty steel skeleton is becoming as brittle as old bone, all while remaining completely hidden from view. And all the while, the fungus itself wages a third kind of war, a war of pure physics. As the mycelial network grows, its individual threads, the hyphae, swell with water, generating incredible internal force. This is turgor pressure. At the very tip of a single microscopic hypha, this pressure can reach up to 8 megapascals. That is over 1,100 pounds per square inch. It is the equivalent of a grand piano balancing on the head of a pin. Now, imagine millions of these pins all pushing all the time from inside every microscopic crack and fissure in the concrete. Each tiny flaw becomes a beachhead for this relentless biomechanical jackhammer, which patiently and unstoppably wedges the city's foundations apart at a microscopic level. This is the genius of the biofilm. It is a symbiotic superorganism, a multi-front assault team. The fungus acts as the logistical backbone and the physical shock troop. Its mycelial network is the circulatory system, drawing sugars and carbons from a nearby plastic conduit and delivering this energy to the bacterial specialists on the front line. The acidophiles are the sappers, chemically melting the concrete defenses. The SRBs are the saboteurs, neutralizing the steel skeleton. Each member of the biofilm works in perfect concert, creating a cascading failure where one action enables the next. It is an attack of such complexity and efficiency that no single organism could ever hope to achieve it. So the city waits. It stands tall against the sky, a monument of hollowed-out strength. Its foundations have been turned to powder, its steel bones are riddled with holes, and its entire internal structure is being held together by a fragile web of fungal tissue. It is terminally ill. The metabolic activity of the trillions of microbes waging war within its walls is even generating a faint, almost imperceptible heat, a low-grade fever running through the concrete veins of the metropolis. The city doesn't know it yet, but it is already dead. It is a ghost, a hollowed-out shell, waiting for the one final breath of wind, the one extra drop of rain, that will finally push it over the edge into a final catastrophic collapse. The end does not begin with a bang. It begins with a groan, a low, resonant hum from deep within the steel heart of a suspension bridge, a sound so alien and profound it is felt more than heard. For a century it has stood, a monument of engineering, its cables elegantly draped, its towers defiant. But for years, the silent sickness has been hollowing it out. Today, a day like any other, under the mundane weight of morning traffic, the cumulative strain of a million tiny, internal failures finally reaches its breaking point. The city is about to discover the price of its unseen infection. The science of this moment is brutal and simple. Reinforced concrete is a partnership. The concrete provides compressive strength, the ability to withstand crushing forces, while the steel rebar inside provides tensile strength, the ability to bend and stretch. The fungal biofilm has systematically destroyed both. Its acidic secretions have turned the concrete's binding agent to powder, erasing its compressive strength. At the same time, its bacterial symbionts have riddled the rebar with corrosive pits, annihilating its tensile strength. The partnership is broken. The structure is a fragile ghost of itself, held together by little more than memory and gravity. The first domino to fall is a single suspension cable, thick as a man's waist. Deep inside its anchorage, where moisture has pooled for years, the steel strands have been reduced to brittle threads of rust. With a sharp crack that echoes like a rifle shot across the water, it snaps. The colossal transfer of energy is instantaneous. The load it once carried, thousands of tons, is violently shunted to the adjacent cables. But they too are weakened and they cannot take the strain. A resonance cascade begins, a shock wave of failure that rips through the structure at the speed of sound. One after another, the cables pop in a horrifying, explosive sequence, the bridge groaning in protest as its primary support system vanishes. For a few, terrifying seconds, the bridge hangs in the air, a dying beast. The roadway, now unsupported, begins to sag violently, buckling and twisting in a way its designers never imagined possible. The two main towers, now under an impossible, unbalanced load, lean inward. Then, with a final, deafening roar that drowns out the screams of 1,000 people, they give way. The entire structure peels apart, disintegrating into a storm of concrete dust and twisted steel. It does not fall into the river. It dissolves into it, leaving behind nothing but a boiling cloud of debris and a profound, echoing silence. The city's largest artery has been severed. This single catastrophic failure is the starting gun for a citywide collapse. The bridge carried more than just cars. It was a conduit for the city's nervous system. The snapping cables severed the primary power and data mains for the entire downtown district. The lights go out. But more importantly, the electric pumps that keep the city's vast subterranean world dry fall silent. The subway tunnels, the underpasses, the deep building foundations, all of which were already damp and heavily colonized by the fungus, begin to flood. This sudden, massive influx of water is like pouring gasoline on a fire. The fungal colonies, supercharged by the new conditions, explode in a frenzy of growth. This explosive underground bloom has immediate, terrifying consequences for the world above. The foundations of the skyscrapers, already softened and weakened, are now sitting in a swamp of hyper-aggressive fungal growth. The support columns in their basements, their internal rebar hollowed out and their concrete shells turned to chalk, are subjected to a final, unbearable load. They don't bend, they shatter. This is sheer failure, a sudden, brittle collapse with no warning. A 50-story building, its internal supports giving way in a fraction of a second, simply slumps into its own footprint. It is a controlled demolition with no explosives, a vertical pancaking of floor upon floor, driven by gravity and biology. Now, the true horror of the situation reveals itself, the positive feedback loop. Every single collapse, every building that falls, every road that buckles, is not an end. It is a new beginning for the fungus. The mountains of rubble create a paradise of surface area, moisture, and oxygen exposure. The destruction actively fuels an even more ferocious wave of growth. The fungus, which had been slowly, vegetatively spreading for years, is now triggered into a new phase of its life cycle: reproduction. It is no longer just eating. It is breeding. From the rubble fields, new structures begin to rise. Not of steel and glass, but of living tissue. Vast, fleshy, alien-looking fruiting bodies, some the size of cars, erupt from the ruins, their surfaces glistening with moisture. They are the reproductive organs of the new dominant life form on Earth. They unfurl and release their payload, thick, black clouds of trillions upon trillions of spores. The spores rise into the sky, so dense they blot out the sun, turning day into a perpetual twilight. The city is no longer a ruin. It has become a substrate. It has become a fungal garden, a planetary-scale nursery for the organism that has consumed it. The age of humanity is over. The age of the petromyces has begun. The age of chaos eventually subsides. The spore storms that blackened the sky have settled, and the last echoes of crumbling towers have given way to a profound and unsettling silence. The cities of humanity are gone, reduced to vast, mountainous boneyards of concrete and steel. But this is not an ending. The world is not dead. In fact, it is about to be reborn. The fungus, having consumed a civilization, now begins its true and final work. It transitions from destroyer to architect, and the ruins of our world are its raw materials. The first stage of this new creation is a great planetary detoxification. For a century, our urban centers have been toxic hotspots, saturated with heavy metals like lead, mercury, and cadmium, and contaminated with the soup of industrial chemicals. The Petromyce S network begins the cleanup. Through a process called bioremediation, its enzymes systematically break down the complex, toxic hydrocarbons in plastics, oils, and solvents into simpler, inert carbon compounds. At the same time, its vast mycelial body performs chelation, actively absorbing heavy metal ions from the soil and sequestering them within its own tissues, locking them away where they can do no harm. The fungus is not just covering our mess. It is actively healing the poisoned land. As it detoxifies, it also builds. This is petagenesis, the birth of a soil. The fungal network, now miles wide and hundreds of feet deep, becomes the foundation for a completely new kind of earth, a technosoil. It is a bizarre, dark, and rich substrate, a composite of organic and man-made matter. It is composed of the decaying fungal biomass, pulverized concrete dust, flakes of rusted steel, and pulverized shards of glass and ceramic. This new soil is incredibly high in calcium, silica, and iron, but it possesses a chemistry utterly alien to any natural ecosystem that has come before. It is the unique geological fingerprint of our civilization's final passing. Into this strange new soil, life returns. The first to arrive are the pioneer species, carried on the wind. These are not the familiar weeds of our time, but highly specialized extremophiles. Lichens that can thrive on the high pH of the concrete dust, and hardy mosses that have evolved a tolerance for heavy metals. They are followed by calciphilic or lime-loving grasses and wildflowers, plants that flourish in the calcium-rich soil left behind by the dissolved foundations. Their roots, tough and tenacious, weave through the rubble, anchoring the new earth and beginning the long, slow process of primary succession. But these plants are not alone. They are participants in the greatest symbiotic partnership on the planet. The Petromyces network is not just passive soil. It becomes a vast, continent-spanning mycorrhizal network. Its mycelial threads fuse with the roots of the new plants in a revolutionary partnership. The fungus, with its powerful enzymatic arsenal, can extract phosphorus, iron, and other vital minerals directly from the concrete and steel rubble, nutrients that would be inaccessible to any plant. It trades these scavenged minerals to the plants. In return, the plants, through photosynthesis, provide the fungus with the one thing it cannot make itself: energy in the form of sugars. It is a perfect symbiosis, a new global superorganism where our recycled civilization provides the minerals, the sun provides the energy, and the fungus is the engine that connects them. With this powerful engine driving its growth, the new wilderness explodes. Fast-growing trees, their genetics forged in this strange new world, take root in the ruins. Their roots wrap around rebar skeletons, their trunks growing from the shattered husks of office buildings. A new vertical jungle is born. The concrete canyons of our streets become river valleys, their sheer walls draped in curtains of vines. Elevator shafts exposed to the sky become perfect, sheer-faced waterfalls. The vast, dark spaces of underground parking garages, now filled with water, become cave ecosystems teeming with blind, colorless life. It is a world of impossible, breathtaking beauty, a living wilderness growing from the corpse of industry. And where there is a new wilderness, new animals will follow. With the most abundant food source on the planet now being the tough, mineral-rich biomass of the fungus, a new kind of herbivore evolves. Imagine a lithivore, a sheep-sized mammal with continuously growing, carbide-hardened teeth, built to gnaw directly on the tough, semi-petrified fungal fruiting bodies. And where herbivores thrive, predators will evolve to hunt them. Imagine a vertigo stalker, a sleek, cat-like predator with elongated limbs, semi-opposable thumbs for gripping rebar, and a prehensile tail for balance, perfectly adapted for hunting in the treacherous, three-dimensional ruins. Evolution is filling the gaps, and the results are unlike anything that has come before. So, in the end, life has not erased our legacy. It has absorbed it. The carbon that once made up our plastic bottles is now in the leaf of a tree growing from the 80th floor of a dead skyscraper. The iron from a fallen bridge is now a vital nutrient coursing through the veins of a creature we would never recognize. We saw ourselves as the pinnacle of creation, but we were just a geological event, a brief, explosive flourishing that created a new type of rock, a new type of food. Life, in its infinite, patient, and creative power, simply found a way to add us to the menu. And as this new world thrives, you have to wonder, what other bizarre giants and terrifying predators will arise from the ashes of our world?